So we're going to work our way through Chapter 10, and Chapter 10 is going to be discussing gases, and I'm going to likely break this recording apart into several different pieces, just so we don't have to sit here and listen to 3 solid hours or however long it's going to be of me droning on about gas laws. Now, Chapter 10, we are going to be talking about the properties of gases, and we're going to talk about one very important equation, which pretty much for the general chemistry sense covers everything that we'll need to know about gases. Now, a couple of these things that we already talked about throughout the semester is just kind of reviewed here in the first few slides. And gases can be compressed, right? And what that basically means for us is that there's a lot of space, empty space in a gas, right? So for our thoughts or how we look or view a gas, it's basically independent molecules kind of zipping around with high speed and not really interacting with each other. So there's a lot of space in between all the molecules. This is opposed to something like a solid where molecules are sitting very close proximity to another molecule. And so you can't really compress a solid, right? There's not much empty space to kind of smush things closer together with. But in a gas, there's basically a lot of empty space, and so we can talk about them being compressed, right? So we're going to talk about pressure, right, is something that we'll be discussing. Gases expand into any available volume. We are going to assume, right, that if we are examining a problem or examining let's say, a feature of a gas, a property of a gas, that if we put it into a 20-liter container, for instance, that gas is going to occupy all 20 of those liters, right? So that's just one of the assumptions that we make, and it's a good assumption also, right? Gases are completely miscible. Uh, if you mix 2 or 3 or how many component gases together, they're going to make an immediate mixture. This is as opposed to a liquid where sometimes you have to like stir things around or mix things up or shake it to kind of get a solution to form. But we will assume that gases are completely miscible and that they instantly are uniform throughout. And we're at the bottom point here, we're going to use terms of temperature, pressure, volume, and moles, right? So remember, N is the ever-present moles, right? So we're going to use all these different ideas here to kind of come together with some equations to talk about gases. So real quick, what is pressure? Well, pressure is just a force applied over an area, right? So a force applied over an area, and we can even expand out the equation of force there to mass times acceleration. And that's a little bit beyond what we need to talk about here in this class. Just, I think if you guys, or for argument's sake, for simplicity's sake, when we're talking about pressure, we're talking about basically applying a pressure, not as in pressure as in, the pressure you feel to pass this course, right? So force over an area. Now, what is immediately relevant to us are the units that we will see. Right, if you look down here, you see there's quite a few different units for pressure. Most commonly, we're probably going to be dealing with bars, atmospheres, right? But there are a couple other things. Now, I don't need you guys to memorize these, right? But these are important relationships to know here, right? How many atmospheres are in a bar and how many atmospheres to torrs and to millimeters of mercury. If you were to say, what are the most commonly reported units, I'd probably say atmospheres or torrs or millimeters of mercury there. So any of these units, if you see those, we are just referring to pressure. Okay. Kinetic molecular theory, this is something we've talked about quite exhaustively throughout the semester. So I'm not going to sit here and read through this wall of text, right? Just a couple of important things, right? The assumption here at the top is going to be very important. A gas consists of tiny molecules in rapid random motion, right? They're small compared to the distances in between them, right? That's what we just talked about with being compressed. They mix completely. They move randomly at high speeds. They're not really, there's no real molecular interactions with them, and that we assume that they make elastic collisions, aka we don't have to worry about, well, let's call it the actual physics, right? And if we want to summarize some of this in one sentence or one word even, we're going to assume that gases have an ideal properties with them, right? They're going to behave in ideal manners. And so in a minute, we're just going to be talking about something called the ideal gas law. And we should understand that when we're talking about ideal gas laws, we're not really talking about an actual view of reality, but we're talking about something that's very close, right? In actuality, gases do interact with each other to a certain extent. It depends on the type of gas and, how big of a container it's in, and is it compressed in heat, right? A couple of other things. And we will look at an actual example of this way towards the end of this chapter, right? But for the moment, we're just working with, let's call it, ideal situations. Okay. Um, Again, I'm not interested in reading out my slides to you guys verbatim. These slides are available for you, online. Uh, Here's the only part that I want you guys to really pay attention to, right? The average kinetic energy is proportional to temperature, right? So as you add more temperature, right, if you want to think about it like that, as you increase temperature, you increase the speed. Well, that shouldn't shouldn't be too shocking of a statement, right? If we're increasing temperature, we're basically just increasing energy, right? And that energy has to go somewhere, and it goes into the energy of motion, or part of it at least goes into the energy of motion. And if we take this idea and kind of graph it out, right, we are looking at oxygen gas, right? We're looking at oxygen gas at 25, right, degrees Celsius, right, and then at 1,000 degrees Celsius. And you can see that the average molecular speed increases, right? So higher temperature equals higher speed, right? That's the only point that I'm trying to make here with this. Now, it's not only the temperature that we have to pay attention to at least. It's also mass that has an impact on, let's say, the average speed of a gas. The heavier the gas, the slower it's going to move on average, right? Relatively slow, I should say, right? So if we compare oxygen versus nitrogen, right, versus water versus helium, right? So as we increase mass, we see that the average speed slows down, right? So if we go from small weight, right, a small molecular weight at helium up to a larger molecular weight up at O2, right, then we see the average speed decreases as we go through that. And now this has something that's pretty relative to, or something, not say relative, something very important if you're interested in things like diffusion and effusion, right? So there is let's call it a equation to calculate effusion here. And an effusion rate is proportional to, right? So we're just talking about proportional, right? Proportional to 1 over the square root of the molecular mass, right? So if we just do a quick equation here, right, a quick calculation, if we compare helium to nitrogen gas, right, helium effuses 2.6 times faster than nitrogen does, right? Helium's moving around faster. It's a smaller molecule. It's just easier for it to kind of escape. Let's say it's the balloon, right? It's easier for helium to get through the tiny holes that are in the rubber of the balloon there, right? So it's easier just to get through that. So if we want to calculate a fusion rate, it's a simple proportional factor here, 1 over the square root of the mass of whatever it is that we're looking at. All right, so now let's get back into this discussion of ideal gases. So any equation relating volume, pressure, temperature, and moles is a gas law. Okay, most gases at room temperature and pressure are ideal, right? And remember, just a couple slides ago, we talked about what assumptions we are making when we say the statement ideal. Okay, extremely important, right? Extremely important. So big stars in your notes here, whatever you want to say, always use the Kelvin scale of temperature. We're often going to be dividing by temperature, and obviously we can't divide by 0, right? And Kelvin is the only available scale of temperature for us that does not contain a 0 to any, let's say, appreciable degree. Obviously, there's such a thing as absolute 0, but for anything practical, right, nothing, or we assume that nothing happens at absolute 0, right? So always use Kelvin. Always, always, always use Kelvin. Always Kelvin. No Celsius. Okay, no Celsius. Got it. All right. First law that we talk about is something called Boyles Law. And Boyles Law basically states that volume varies inversely with pressure, right? So again, we see that volume is proportional to the inverse of pressure, right? Volume is proportional to 1 over pressure. And if we do a little bit of rearrangement here, right? If we do a little bit of rearrangement, some subtle math, right, we get to an important law, right, where P1 V1 equals P2 V2, right? So if we're comparing pressure and volume at two different states, right? So for instance, it could be a question like if we have, let's say we have pressure at a 100 atmospheres, right? We have a volume of 20, right? P1 and V1, right? We could calculate P2 and V2 if we had the appropriate data, right? So if we assume we have a gas at 100 atmospheres in a 20-liter container, I could ask what volume would it take up if we increase the pressure to 200 atmospheres, right? What would the volume be at that point, right? So that's how we use that. This is a typical question for Boyles Law. And don't worry, we'll do a couple more examples later, right? So I'm just walking you through what the different variables mean at this point. So Boyles Law is used to compare, right, changing pressure and volume for a system. The assumption that we make is that temperature and moles must be held constant, okay? Temperature and moles must be held constant. Another way that you might see this written is PIVI equals PFVF, where initial, right, where I is initial and F is final. So initial pressure and volume equals final pressure and volume, right? So if we're changing the pressure, the volume of a given system, right, this is where we use that equation. Charles's law, right? Charles's law is basically telling us that volume is proportional to temperature. And again, we have to make the assumption, or not make the assumption, we have to hold pressure and moles constant, okay? So if pressure and moles are held constant, volume is proportional to temperature, right? Directly proportional is what we could say here in this case, right? So volume is proportional to temperature, and if we do a little bit of a rearrangement, we again get to a very useful condensed equation here, where V1 over T1 equals V2 over T2. And again, we could make the same kind of arguments as we did on the previous slide there. If I give you a volume and a temperature, we can calculate the change in volume or the change in temperature if we have the information, right? So again, we could, rewrite this, and you see it rewritten sometimes like this, where initial volume over initial temperature equals final volume over final temperature. So if a problem's asking you to calculate volume as you change temperature, what it's asking you to use is Charles's law. Avogadro's law, often confused with Avogadro's number, right? Not the same thing, right? Avogadro's law is a relationship between volume and moles, okay? So for an ideal gas, volume is equal to a constant times the number of moles, okay? And so if you take a look at the picture, right, we have three different gases, helium, methane, and oxygen. Volume is 22.4, right? At 1 atmosphere at 0 degrees Celsius, 0 degrees Celsius, we could say 273 Kelvin, right? Right, same thing here, right? And it's equal to 1 mole, okay? And if you look at the top for all these gases, right, all these values here are essentially the same, not essentially, they are the same, right? So 1 mole of any gas at standard temperature and pressure, right, is equal to 22.4 liters. And that's an important number to know there, right? And then on the next slide here, we'll just walk through how we get that, right? And it'll be our first example, or we'll walk through how we get that number, right? But any gas at standard temperature and pressure, which is 0 degrees Celsius or 273 Kelvin, right, and 1 atmosphere is equal to 22.4, right? And if we look down here, here's Avogadro's law, right? V1 over N1 equals V2 over N2, right? Initial volume over initial number of moles equals final volume over final number of moles. One last thing to pay attention to, all right? So at constant temperature and pressure, the volumes of reacting gases are always in ratios of small whole numbers. And essentially what this is saying is that volume is proportional to the number of moles, okay? Volume is proportional to the number of moles. Essentially means this, right? If we have a balanced chemical equation, right, our stoichiometric coefficients are approximately equal to, right, or not approximately, we can assume that they're equal to the number of liters of those gases present, Okay. Now we are making some assumptions with all these cases, but just something important to recognize. Okay. If we're dealing with gases, we can assume our stoichiometric coefficients are equal to volume. And if we take all these ideas together that we just talked about, Boyles Law, Charles's Law, Avogadro's Law, and we mix in a little bit of that combining volumes idea there, right? We're going to get to the ideal gas law, PV equals nRT. And this is the equation that you need to know. Okay, this is the equation that you need to know. 95% of the stuff that we're going to be calculating in this chapter, we're going to be using this equation right here, right? Ideal gas law. So the ideal gas law, what are the different parts of it? Well, P is pressure, right? V is volume, N is moles, T is temperature in Kelvin, and R is an ideal gas constant, which I think if the last time I looked on Wikipedia, there's something like 38 ideal gas constants. I mean, there's different situations where you use different gas constants. By far, we're probably going to be using these the most in this class, those four. Again, you don't need to memorize these. I'm just saying, hey, if you're working on some practice problems, if you're working on your homework, if you're on an exam, if you're on a quiz, these are probably the four most common ones that you're going to end up seeing, right? That's all I'm really saying with this, okay? But what is important to recognize are what are the units, right? Liters, atmospheres, mole Kelvin, liters, bars, mole Kelvin, liters, torrs, mole Kelvin, and then number four there, joules per mole Kelvin, okay? So different units for different applications. That's what we need to get. That's what we need to do. Okay. So pressure times volume equals moles times a constant times temperature. All right. So let's quickly do one example of just how to use apply ideal gas law right to a simple problem, and then we will end part one here, and then we will move on to part two where we start to look at some more practice problems and things like that. Okay. So just a minute ago, we said that 1 mole of an ideal gas, its STP, occupies 22.4 liters. And so we just want to prove that that is true. Okay, so to prove that that is true, we're going to use our ideal gas law. Okay, and we're going to need to know that standard temperature and pressure, right? Standard temperature and pressure is equal to 0 degrees Celsius and 1 atmosphere. Okay. That's not me making that up, right? It doesn't say Dr. H's temperature and pressure, it's a standard temperature and pressure, right? That's the assumption. So what we need to do is convert Celsius into Kelvin, right? So 273.15 Kelvin, and atmospheres is just fine. So let's collect our data. We need to know P, V, N, R, and T, right? We have an equation that has 5 components. We need to know 4 of them to be able to solve this, okay? We are given information about temperature. Temperature equals 273.15. Whoops, excuse me, 0.15 Kelvin. R is a constant, right? Given that we're units of Kelvin and atmospheres, right? If I scroll back up here, Kelvin, atmospheres, right? So I'm going to be using this constant right here. 0.08206 liters, atmospheres, mole, Kelvin. There's the units. So we got T, we got R, N equals 1 mole, right? That's the information that's given right here. V is what we're trying to prove, right? We're trying to prove that it's equal to 22.4. And pressure equals 1 atmosphere, okay? So I just got my table of data. You'll see that when I go through and solve these problems, I always make a table of data. The reason why is because usually there's a lot of numbers thrown at you in this chapter, right? And so organize your data is what I say, okay? So once we got our data kind of all set, right, let's rearrange our equation. We need to solve for volume, so I'm going to divide by pressure on both sides. So volume equals nRT over P. And now I just fill in my data here, right? N is 1 mole, R 0.08206 liters atmospheres, mole Kelvin. T 273.15 Kelvin over pressure, which was 1 atmosphere. Okay. And if you plug this into your calculator, right, you'll get volume equal to 22.4 liters. Okay. So if you're on an exam and you forget this 22.4, right, just remember what standard temperature and pressure is, 0 and 1, right, and then, right, 0 for temperature, 1 for atmosphere, right, for pressure there, right, then you can calculate this 22.4 out of it. Okay, that's the end of part 1. We'll come back and continue on in part 2.